I'm just gonna start. You know, there might still be a couple of people coming in.
Alex isn't coming in, just not very well.
Okay. So I'll just remove the bottom bar.
Lecture 10.
Lecture 10, yeah. So last week lecture 9, 10, 11. So one more after this, and you're done. So we have 2 more sessions, and they're covering multi-level models. And after those 2 sessions, you'd be able to complete the assignments. You won't be able to do the entire assignment yet after today, but you can do bits and chunks and as you move along. And today we'll look a little bit more at multi-level models, which some of you might use. So last lecture we talked about structural equation models and mediation, testing mediation models with those structural equation models, and also seeing perhaps even models where you combine both confirmatory factor analysis and mediation. And today we'll talk about multi-level models, which some of you might have come across. So the goals for today and also perhaps for next week are multi-level models. I won't be able to make you a multi-level expert, so as with structural equation models, so I would take an entire separate course. So other universities have an entire separate course on multi-level models, and I'm trying to squash everything in 2 lectures. So it will just be the highlights. So the idea is that you have an understanding when you come across it, and that you're able to build very basic multi-level models yourself. Same as with structural equation models. So some other universities would have an entire course just on multi-level or on structural equation models. And you're sort of getting the quick highlights of what it means in R and how to do it. So for the assignment after today, you should be able to complete multi-level models. Some bits are still following from next week, such as plotting it and some other things. You should be aware that also one of the benefits here is that you can do some basic multi-level models with SPSS, but you would have to leave it for another package if you were to do more complex multi-level models. So if you have crossover effects, and I'll explain to you in a bit what those are, or if you have multiple levels, let's say you have 3 or 4 levels, then SPSS can't do it. So you would have to switch to another package anyway. And the most common packages are MLWin, like SPSS can do to a degree, but it can do some more complex models, SAS, Data, and HLM. So those are multi-level models, but R can do all sorts of multi-level models as well. So that's one of the benefits to do it. Again, as we've also come across, there are many different ways to do the same thing in R. So you can do multi-level models in multiple ways. And I'll just teach you 2 packages, which are LME and NLME. And I'll focus mostly on LME. But you should be aware that there's many options to do multi-level models. You can do Bayesian regression models, Bayesian multi-level models. I won't talk to you about any of those today. So, why would you use multi-level models? Group data are everywhere, and even though we've casually assumed that you have independence, most of the time, unless you experimentally assign people, in reality you might not have independence because people are from the same backgrounds, they are from the same school, or the same class, and even though you assume that data points are independent, there might be some lurking third variable which explains part of the course you're interested in. So if you have experimental control, you randomly assign people to experiment or control, then you sort of have tried to guarantee independence in that way. But in many situations, that won't be possible because you're going to schools or you're going to hospitals, and the data is clustered by nature because they are part of the same school, part of the same class, part of the same hospital, part of the same therapist group, part of the same organization, and so you can't just rely on independence. So some examples of applications. So you have children in classes in schools. So there you would have individual children nested in classes, which are in turn nested in schools. You could have employees in departments in companies, for example. So they're not independent data points because their responses on, for example, a survey of well-being would be influenced by the department they're in or by the company they're in. And so you might want to take into account the fact that they're non-independent data points. And you recall from regression that it was one of the assumptions. So all the data points are independent and you have no sorts of issues. But in this case, you have clustering, and there could be further clustering because companies are part of the same region, for example, and companies from one region might respond very differently to companies from a different region. And the thing you might be attributing to your survey or your things could be caused by regional differences or regional effects. And if you don't account for that, you'll be making wrong inferences. You would be saying this variable is related to this variable, but in essence, it's just due, for example, to the fact that cultures differ in how individualistic or collectivistic they were, and you didn't account for the regional differences between those companies nested in different regions. Does that make sense? So individuals can be nested in neighborhoods. So in many health applications, we're interested in trying to understand if there's neighborhood level effects. Those neighborhoods in turn are nested in provinces or districts or some larger units. And those, then you move a level up, you have countries, and countries are nested in regions. So you have lots of nesting that could be going on. In some cases, for example, in health behavior, we believe that the neighborhood has an influence in how people behave. And that's classical psychology theory, so it's not just an individual with their personality, but it's also the interaction between the environment and the individual. In order to really get at that, we would need multi-level models in order to understand the interaction of the environment on the individual to create certain health outcomes or to create certain psychological outcomes. We would need a multi-level model. Yeah. Individuals, so some of you might be doing research on couples or family dynamics, and those individuals are also not independent. The basic reason could be genetics. Yeah, so they're all related to one another. So that's one reason. And the other thing is that you want to account that you want to, for example, track that people are part of the same couple. Their responses might be influenced by being specifically linked to that couple and the couple dynamics. And so you want to account, some cases you want to also use that couple of analysis to explain some of the behaviors you see in couples or in families. But at worst, it's noise, and you want to take into account the noise. You want to make sure it's not simply due that husbands are giving responses as a function of their wives, or vice versa, so you want to account for that. So that's why you would need a multi-level model. If you would treat husbands and wives as all being independent data points, you would ignore the clustering that is going on. Patients assigned to the same therapists, and you can then also have therapists nested in hospital. So when you're doing an intervention, often you might not have full control, and patients are clustered in therapists. So you might assume that they are independent data points, but they're not, because they all have in common that they're going to the same hospital or to the same therapist. And if you don't account for that, that would influence your design, that would influence the conclusions you make. You might say, I'm a complete experimentalist, so none of this applies to me because I have full experimental control because I randomly assign people. But you could also have noise associated with stimuli or with block sets. So you might want to partial out the fact that your stimulus has some noise attached to it, that everybody's seeing the same stimulus. And we could model that with multi-level models as well. So in this case, either the stimuli are nested in blocks, so you take into account the block structure, or you can take into account the fact that you can model in the sense that the stimulus is the thing with all the individuals' responses being nested underneath it. So every stimulus is the top level, so to speak, and at the bottom level you have participant responses. In order to account for the fact that some stimuli might be better than other stimuli, for example, or they might be cleaner, or it might have less noise, or they might be better calibrated, but they're not the thing you're interested in. You're interested in the manipulation you made, for example, brightness or coloration or something else. So in order to account for those type of things, you would model the noise associated with that stimulus, and that would give you cleaner estimates of what is happening to your experimental variable. Yeah, it would parcel out any type of noise associated with the stimulus. And so also commonly you might have longitudinal designs or block designs, and I'll talk to you more about those next week. And then you can use multi-level models to account for some of these things. So the unfortunate thing is that when people speak of multi-level models, it's people don't use consistent terminology. So hierarchical models, random effects models, random coefficient models, mixed models, hierarchical hierarchical linear models. These are all terms associated with multi-level modeling, and people are not interchanging between those. So I'll also use some of these terms interchangeably, but when you come across a paper and it says a mixed effect model, you need to think of it as a multi-level model. Yeah, and similarly, when you come across something which says random coefficients, it's a multi-level model to some degree. Yeah, that will help your understanding. So why again would you use this? And I'll try and convince you first and foremost that multi-level models are a good thing to have, and I must say I'm biased because I've written about multi-level models and you should use them and all sorts of other things. So very simply put, depending on the level of analysis, you can get very different results. So if we analyze, for example, the results at school level versus at individual level, we could draw very different conclusions. And multi-level models are sort of the only way in which you would be able to account for effects occurring at different levels. And it sounds quite fluffy perhaps now, but I'll try and give you some examples as to how it works. So for example, different levels of you could have a question about a group level type of dynamic, but you could also have a question about individual level dynamics. And so you could draw wrong inferences if you would take the group level to infer what's going on at the individual level. So sometimes people do this. For example, you see these charts on, let's say, religiosity and homicides, and you can plot all the countries, and you could get a nice regression line showing that countries which are more religious have more homicides. Does that mean that more religious people are more likely to commit homicides? Not necessarily so, because we've made a leap from that group level at country level to the individual level. And that doesn't necessarily have to happen. So the pattern at the individual level could be very, very different compared to the aggregated level. And that might sound like some type of magic, but it is pooling fallacies. And it's basically when you aggregate things, the patterns might start to look very different. And I have an example to show you in a bit. So one of the famous examples is from 1950, is Robinson, and deals with literacy and migrants. And so if we take a score for every single state, we can find a positive relationship between the proportion of migrants and literacy. So a positive correlation, a very strong positive correlation between the proportion of migrants and literacy. Does that mean that migrants are more literate than locals? No, but you would draw the erroneous inference from that graph. You would say, so that must mean that migrants are more literate. No, they're being sucked into regions where literacy rates are higher because there's more jobs or more opportunities or more economic opportunities. But just from studying the aggregated graph, if you would then leap to the individual level, you would say this means that migrants are more literate. Another famous example is suicide rates and religiosity. So I'm not sure if you know, but under Catholicism, it's not very good to commit suicide. You're committed to eternal hell and damnation. And Protestant views are more lenient in terms of what happens to you in the afterlife in terms of suicide rates. So if you look at regional level, you can find positive associations between the proportion of Catholics and suicide rates, but that doesn't mean that the Catholics are committing suicide. It's actually the Protestants committing suicide, leading to higher proportions of Catholics. So that creates an erroneous relationship at this group level. And if from the group level you would draw on a strong relationship between these two variables, you would then make an erroneous inference to the individual level. So this is something which is quite often overlooked. So the relationships at the group level can be very different than at the individual level. And also, you could take one step further, and this is the within individual level. So the patterns within individuals, so you answering a questionnaire over time could be very different than the patterns between individuals. So suppose you have an example where people are completing a survey on personality on different times, as well as how much coffee they consume. You can find a very different pattern within individuals on like how neurotic they are when they consume coffee versus between individuals, which is the amount of coffee people consume and their average neuroticism score. So it could be very well the case that every single time I drink a cup of coffee, I become slightly more neurotic. But at the aggregate level, between individual differences are so large, it drowns out any type of relationship between coffee consumption and neuroticism. So different levels of analysis lead to different conclusions. So everybody sort of get this point and why this is important. And it's most of the time because I deal with country level data and all sorts of things. I'll give examples like that, but it also applies to within versus between subject designs, for example. So this won't be very readable, but you can probably see it better on your screens. But we have here, let's say, 3 different monkeys, and every monkey within the individual has a negative downward trend. But if we average them, we find a positive relationship between those relationships. So what you could find, for example, to stick with the example of monkeys, is that you could find a correlation between monkeys on nut cracking and rainfall, but it doesn't mean that your monkeys are cracking nuts in the rain. Yeah. So pulling across all these different monkeys, you would find a positive association between average rainfall and nut cracking behavior, but within each individual you'd find no relationship between nut cracking behavior and rainfall. That sounds counterintuitive, but it happens because of these pooling fallacies, because when you aggregate data, patterns might reverse, and it's known as reversal paradoxes, Simpson paradoxes, all sorts of pooling fallacies. The reverse is that you would infer what happens between individuals based on these on what's happening within individuals. So that's the atomistic fallacy. So one is the ecological fallacy, the other one is the atomistic fallacy. And so not only happens between and within countries, but for any type of thing where you do some type of aggregation or create a score, you can have these type of pooling fallacies occurring. And one remedy is multi-level models to these type of pooling fallacies. Does that make sense? Even though it's monkeys, but so in case we're not convinced, there's some further good reasons to opt for multi-level models. They're from a guy who wrote the MLWin program, so you can click on the link. So I've just copied that from there. So correct inferences, that was what I was banging on about. So traditional multiple regression techniques treat units of analysis independent observations. Often that's not the case. If there is a hierarchical structure, then your standard errors of regression coefficient, so the SE, so the B's will be correct, but the standard errors will be wrong, and likely they'll be underestimated, leading to an overstatement of statistical significance. So if you went out and you did your study in a school and you didn't account for clustering based on classes, for example, then you might say there is some type of relationship, but it's entirely driven by the hidden structure of classes in your data. Yeah. So sometimes we're just really interested also in group effects, and in regression at the individual level we can't get very far. So we can get we might be very difficult for us to identify outlying groups, and so sometimes, for example, in the context of school performance, we might be interested in seeing if some schools are really better schools, and in that case, it's a multi-level type of question where we get the residuals and then see if we partial out people's start individual scores. Do people have a significantly higher score? Is there a pattern in this trash bag where they're significantly higher for one school than for the other school? And that's a multi-level type of question. And you wouldn't be able to get at those type of questions very easily with just regression. So if you want to find out if one hospital is better or worse, or one school is better or worse, or one department is better or worse, those are the type of methods you would need. So in this case, it would be school-level residuals in a multi-level model adjusting for the prior attainments of the pupils, so their intake scores. More reasons to opt. Lots of text, so my recommendation for post-its doesn't apply to my slides. So, but I do think it's useful here to spell out. So sometimes we want to estimate group effects together with group-level predictors. So sometimes in regression you'll be able to put in dummy variables to say it's part of this class, and so we've accounted for the fact that there are different classes in our school. But then suppose that these classes vary, for example, in mixed gender composition or in ethnic backgrounds, then you wouldn't be able to draw any type of additional inferences beyond the dummy because they're just correlates, a perfect correlate. So in a fixed effects model, the effects of group level predictors are confounded with the effects of group dummies. And so you can't make then further dummies to say it is really mixed sex driving this rather than the school. Whereas in a multi-level model, we would be able to say it is mixed sex, which leads to higher or lower scores above and beyond the class structure that we have. Yeah, and the effects of both type of variables can be estimated in a multi-level type of model. And sometimes we also want to do inferences of to population of groups. So in a multi-level model, the groups are treated as a sample from a population of groups, and you might be able to draw inferences. So with your regression model at the individual level, you wouldn't be able to draw any inferences of what happens in the group level. The best you can do is having these dummies. But it would be very difficult to infer to a population of groups. And in a multi-level type of model, we can infer what's happening to a sample. So we treat it as a sample of groups, and then we can say, does this pattern hold in a population of groups? Yeah. So it allows us to do some type of generalization beyond that. So quite dry. I should also tell you what multi-level models cannot do. You can read a paper on that. So they allow for a more accurate estimation of effects. So if you could, for example, predict If there's a new individual in a certain class, how well would he do? If there's a new class being formed or a new state or something else, how well would it do in terms of performance or economic performance of all sorts of other things? You can use your model to make predictions, but it's often mistaken for causal effects. Same as with these structural equation models. Unless you experimentally manipulate your groups, there is no causality. Yeah. So even though you might say, "Oh, this is really being driven by the neighborhoods. The neighborhood is leading people to smoke or people to have depression." We often lapse into that causal language, but it's really hard to make any type of inferences based on causality just from a multi-level model, because again, it's all correlation. It's all a statistical correlation that we're dealing with. Unless you experimentally manipulate it, you wouldn't be able to find out. Yeah. So again, there are some assumptions. I won't review them everywhere. But it is a regression again. So do you guys remember the assumptions from regression? I already gave away one, which is the non-independence. But some other of the assumptions you might recall. You've done them for your assignments. They were like bullet points in your assignments. So hopefully some of that stuck. Remember some of the tests you did or some of the things you did in order to check for regression? No? Oh, that's bad. Bad for me, but yeah. No, there's nothing that rings a bell in terms of the type of test you did and what you checked in your.
One of them called Welch.
What?
One of them called Welch.
Welsh. No, well, Welsh's test was sort of what you did with Welsh's test on the top of my head is what you did if you had a violation and you would use median things for the ANOVA. So that's a Welsh type of test. So Welsh type test, I'm not sure if that's along the same lines, but you plot it. Yeah, so lots of things we plot. So you recall perhaps that we looked at residuals. Yeah, so we looked at whether the residuals were normally distributed and whether there were any significant patterns in there. By now you should have known about homogeneity of variance and like all these problems of we don't want any funnels in those plots. You recall that? So we don't want any patterns. So we don't want the error to increase or decrease as a function of the predictor. So homogeneity of variance, which is the same thing from ANOVA, is the same. Or heteroscedasticity is the other term, as the term you came across from regression. So linearity, heteroscedasticity, autocorrelation to some degree, but autocorrelation here you can model that also with this, because you could have temporal autocorrelation because you measure the same things in time, but you can allow your model to correct for that and then to model that correlation over time. So usually that's not discussed, but linearity and homogeneity of variance are usually the key things. Also like the distribution of the residuals, the fact that they should be normal looking are the things we might be looking for. I'll give you some examples in a bit. And again, the type of things with outliers, so if you have massive cases, they could be very influential. If you have one outlying school, for example, that could really influence your estimates. Another thing is sample sizes. So it's still an ongoing debate as what sample size you need for multi-level. I've seen also when reviewing papers, I've seen the entire range of like very small samples to very large samples. It sort of depends the level you're interested in. So are you interested in the group level or an individual level? So at which level is your manipulation or your predictor? Are you interested in the random effects? Are you interested in estimating the noise? And because, for example, you want to find out the best school or the worst school, those type of questions influence what type of sample you should get and the size of one level versus the other level. But as with structural equation models, these models tend to be data hungry. So again, think of roughly, you can always sort of use a really quick and dirty rule of thumb, like around 10 per level or 10 per variable is what you would need in order to correctly estimate parameters. Because you're also trying to estimate parameters, and you're asking the model to make predictions from your data, and every arrow, for example, you draw in a structural equation model is something you need to estimate. And the same in regression, you have to estimate every single coefficient. And so that's basically the constraint, because otherwise you'll run into things where it says, I cannot estimate it, or some other issues. Yeah. So you could think of something like if I get around 10 or 15 cases per level, that would be quite good because then we can estimate what's going on in that level. But if you only have 1 or 2 cases to estimate from, the model's not going to do very well because it's just going to take the mean and then gamble. And if you have very extreme scores, it doesn't have a lot to work with to estimate what's going on in group level because it only has 2 data points to estimate. Yeah. And it's further compounded if you have missings, for example, and all sorts of other problems. So if you have very few cases per level to estimate, then you can opt for Bayesian models, and they do better in terms of estimating those group level effects. But I won't tell you more about those, but they come with their own set of challenges. So now we're getting to the R bit. So I'm going to talk to you today about LME4 and NLME. I've also worked with MCMC GLMM, that's a Bayesian way of estimating regression models, and BRMS, which is Bayesian regression models via STAN. And so STAN is another high-end statistical package, and they can do more complex type of models. But if you ever need those, just come and find me and I can give you some things to read. But for now, for most of the things you might come across, also in papers you'll come across LME4 and NLME in terms of our models. So it's up to you to pick. Your results will be roughly the same if you pick LME or NLME. There's some intricacy. So for example, LME4 doesn't print p-values. I'll return to that. NLME does print p-values. There's an entire history and statistical fights behind this, and I'll try and say a little bit about that later. But note that the codes differ between packages, so it's perhaps quite confusing because some of the codes which work for one package don't work for another package because they have different syntax as to how you write the equations. But I'll give you some examples later. Now today we'll work with an example, and unsurprisingly it will be with schools because that's a natural type of setting where you would apply multi-level models. So the dependent variable in this case is a standardized result of a student on a specific exam. So you could think of this as your GCSE or some type of standardized testing at the end of your degree program. It's called norm exam. In estimating the score on the exam, we have 2 levels. We have the student and school. This model doesn't have classes, so you could still have also classes. And on each level, we have one exploratory variable. We have on the individual level, we have the standardized score of the student on a reading test, which is the London reading test. So these are London schools. And on the school level, we have the average intake score from that school as to basically the mean of all people's tests into whether it's a good school, bad school, so to speak. Yeah. So you can have many, many more variables, but we'll start out quite simple. Yeah. So we have some things which are group level variables, such as school average or like SCAV, and then we have some things which are at the individual level, which is LRT, which is the London reading test. Yeah. So we have clear separation between levels. And if you want to find out more, so this is a classical multi-level type of data set, and you can read more about that there. And as you might imagine, especially educational psychologists have been very interested in using multi-level models to see, for example, what predicts student performance, student dropout, all sorts of other things. So this is how you do your multi-level model in LME4. So we load MLRef, and MLRef is just a package which has lots of data sets to use for multi-level models, so you can also toy around with it. We call LME4. We can't make something, perhaps I shouldn't have called it data because data is very commonly used, so perhaps I should have called it exam or something else. But so actually I did call it exam, yeah. So I also, it's also, once you load it, it's called exam, so you can also call just exam afterwards. So this is the code just to load the data. This is a null model, and LMER means that it's like your ANOVA command before or your LM command. So LMER is the wrapper for the function. So this you should by now recall is the dependent variable. Yeah. So the thing before the tilde is the dependent variable. This is just an intercept. So 1 is just an intercept. So first we're going to build a null model, and then we're going to build more complex models. And this vertical dash tells us we are having a random intercept. So we allow schools to vary in their norm exam. So just to quickly graphically draw this. So it means you have parallel lines, and we allow for schools to vary along those lines. So it's not will come to random slopes, which means that those angles will also start to vary. But now we just allow for separation. We allow for some schools to start out higher or lower than some other schools. So this is a very basic model, a random intercept model. And I put in RMEL is false, and I'll explain to you in a bit further what it means. But basically, we can estimate models via maximum likelihood and restricted maximum likelihood. Restricted maximum likelihood is the default because it has much better properties for smaller data sets. But the downside is that you can't really compare some type of model structures with RML. So you can not really. So remember that with AIC type of testing, we always use maximum likelihood, and so that's also what we want to do here. And so we want to use maximum likelihood in order to compare models. But there's some further intricacies to it later. So massive output text again. Sometimes it will overflow, but I'll just again sort of show you. I set it up in a sync so I can show you what happens. Let's go here. So what you get now is your AIC, your BEC. By now they should be familiar from what we got from structured equation models. You also have your log likelihoods. It has some deviance measures. So deviance, if you're a Bayesian, you can also use lots of things with deviance, so don't worry too much about it. Mostly you care about those two because you remember those two from model comparisons from structured equation models. These are the residuals. If you're very clever, you can also already see it should be a mean around 0 and then a normal distribution. Yeah, we'll have some plots later to check, but you can use the scaled residuals to sort of quickly eyeball, and if you find that this is really different from 0, then something has gone wrong with your model and you've violated some of the assumptions, because we should find a nice normal distribution in our trash bag. And so what we then have, this model doesn't have any fixed effects, we only have random effects, so we'll print random effects and we'll print the variance. It will say what's the variance between those schools in terms of having their intercepts high or low. Yeah, and it's basically telling us if there is no substantial variance, it would be 0. So because that means that all the schools, there's nothing happening at school level. And it would also have the standard deviation of that variance, and then the residual is just again the trash bag. So it's how much unexplained variance do you have at this group level. Yeah. It gives you the number of observations. So we have 4,000 students, and we have 65 schools. Yeah. And there's the only thing which we're estimating currently as a fixed effect. We haven't really looked yet at the effect of their intake scores, of an individual intake scores. We've only looked at the intercept, and that's the intercept. And so you can see it's printed a t-value, but it's not printed a p-value. So where's my p-value? So that's quite annoying. We'll come to that in a bit. So that's the output. Any questions on that? So it sort of tells you broadly what you yeah.
I still don't understand what it means by the intercept. Is that between each school on the line?
Yes, so it's just basically allowing, so you can, the degree to which it's allowed to vary. So so if there's, so it's saying if all of them were the same, then we don't need this type of thing. So this is school 1, school 2, school 3, school 4.
All right, okay.
And so you could think of them as 65 different lines, and I'll show you some examples in the end also what it means. So if you would just do normal regression, we would have one line. So we ignore all the schools, and we would just have, based on the individuals, we would have one fit line. What we're now trying to do is we're trying to estimate 65 different fit lines, so to speak, and we allow them to not to vary by angle, but they could shift higher or lower, basically. And for some models that might be sufficient, because people will only, like the schools will only vary up and down, but the more interesting models would also be where the angle changes based on our predictor variable. So that will come in a bit. That makes sense? Everybody sort of gets this? So it's basically we're doing this to sort of see if there's any type of grouping happening in our data. Okay. So I spoke to you about RML versus ML. So we came across maximum likelihood before in structured equation models and also when we were doing factor analysis. So RML has better properties for estimating parameters, and that's been demonstrated. It's much better, but it doesn't allow you to compare fixed effects. So fixed effects is something which is not allowed to vary. So when I say allowed to vary, it means random, and fixed means it's fixed at the individual level. Something can be fixed at the group level as well. It means we're getting one estimate. Yeah? Does that make sense? So it's just terminology. So we can use, when comparing fixed effects, we can use maximum likelihood. So we can make a model with a fixed effect and without a fixed effect, and we can compare the AIC and BEC. So the reason it also doesn't print a p-value is because these people very strongly believe that you shouldn't look at the p-values for the t-tests, but you should build a null model and then an alternative model and then compare AIC, BEC. So that's why they refuse to print p-values. So also because it's not really clear how the p-values are estimated with RML, but that's just another thing. And so remember also that at one point I told you about AIC weights. So we could build many different models, and then we can rescale the evidence, and we can say this model is X times better than this other model. So you might not want to build one model, but you want to build multiple models, and then you can rescale and say the best fitting model is this model, and the other one is this model with like 0.7, 0.3, and then all sorts of comparative evidence. Yeah. If you want to find out more, you can read that paper that I sent you about AIC weights. What we can also do, and I won't go into detail, what you can do is you can average models. So suppose we found some models and they're very close models and we can't distinguish between those. We can average the coefficients from those models and then see what they look like. So because most of the time we're interested in finding whether an effect is significant or not. And so if we have competing models, we can also average those models, and we can use a package to do that. And that's again something I won't show you, but you need to know that it exists, because in papers we will say that they averaged the model. So that means they just took two competing models which are very close in AIC, BEC, and they can't really distinguish, and they averaged them to get average scores for the coefficients, for the intercepts, and the other things. Any questions? Now, the same model in NLME looks slightly different. So in this case, we have to specify what the fixed term is and what the random term is. So it says fixed is norm exam. So this looks again like the equation, but they partial it out by saying explicitly random is this type of effect structure. So in the other one, we didn't have to do this. It was all in one line. Yeah, we just used this vertical dash that you have here. But in this one, if you do that, it won't run. So you have to specify which is fixed and which is random. Yeah. In this case, it's fitted by RML, and you can again use the command RML is false to change that. So this is the output from this, and it should be fairly close. But again, it's sort of it'll print the intercepts, and it won't give you any type of results unless you do summary, and then it will give you further results. So that was not very interesting. We're now trying to build a more interesting model where we have a fixed predictor at the individual level. So remember these type of stand LRT. So do people's intake scores, does it predict how they go out of the school? So does their performance when they go in on this London reading test, does it predict their final scores? And in this case, this effect is not varying between groups. So we're just accounting for the fact that schools consider high or low, for example, on norm exam, because you're going to a very good or a very bad school. But we're not taking into account that the effect of the intake score varies between schools. So it's just accounting for a high or low shift, but not as a function of stand LRT, because that's a random slope model. So it's just accounting for a shift upwards or downwards, but not the angle. Yeah. So we allow schools to vary based on norm exam, but not as a function of stand LRT. So it's just this type of up-type downward shift, but not an angle shift. So no random slopes, just random intercepts. So in terminology, you have a random intercept model and a random slope model. So this is what it looks like in terms of a random. So some of the things have overrun, but doesn't matter too much. I'll show you in a bit also when we, or perhaps I can show you in the actual code. So unfortunately some of the brackets keep on overrunning, but I'll see if I can in the meantime run this. See what it does. So, but we can sort of see what's going on here. So in this case, we've just added a fixed effect. So we've replaced the 1, which was just the intercept for a null model, with stand LRT, and we've used +1 school for this random shift upwards or downwards. We again do RML is false because we might want to compare the models later. It will again print the output, but it won't print the it will print the fixed effect estimate and the t value, but it won't print the p value, because what we're going to do is we're going to compare this model to the other model in terms of AIC, BEC. So these are the AIC, BEC, so you could look at those already and see what's going on. And you can again look at the residuals, and you can again see what's happening to the variance at school level. Yeah. So you can see the t values, but not the p values. And inference is best done other ways. So I would have loved to have p values as well, but they decided against it. And one of the ways of doing it, I'll show you other ways, is comparing models. The other way is to bootstrap the effect. And so you don't have a p-value, but you create a 95% confidence interval for your parameter estimate, as you've done before for some other tests. And then you base your inference based on that. And people have argued that it's a much better way to do compared to just using a t-value in such a model. Okay. So we mostly care about model comparison, and we can again use ANOVA to compare the model. So we have a null model and a fixed predict model. And by now we know this is AIC, BEC. It will print a chi-square, for those of you who still want p-values. And this is sort of like a likelihood ratio test, which you come across also from other things before. Yeah. So this is what we did with structured equation models to some degree. Yeah, you recall that we were also able to compare those type of models. And in this case, you could see it's a big drop. It's going from 11,000 in terms of AIC, and you should know that around 10 is already quite a big drop. And here we go to 9,365. So it really matters if you put in people's baseline scores, so they do predict what's going out. So if people start out with having a good score on longer reading test, they end up with a good score on their exam, on their standardized exam. Yeah. I'll just see if because some of the things tailed off, whether I can still show you, for example, what it looks like. Yes, so this is the so now you can see all my my code as well. So that's a bit which just fell off the slide before. I should have put in a sync, but you would again. So now it's not just printed the intercept, but it's printed a value for standard LRT. And so if it's a standardized score, that usually means they've been rescaled into something you can interpret. And it again prints, so you can see tiny standard error, big t value. So you could already try to infer that it's going to be significant from that. But we do the ANOVA test to really determine that, because you know that 2 times the standard error is sort of the confidence interval, right? Okay, so you can get the range from your effects. So if you have really big standard errors, so you can see this is a big standard error, and that would overlap in terms of the so roughly you could take 2 times this, and then if that overlaps, then likely it's not going to be a significant effect. It overlaps with 0. Yeah.
Do we look at the log likelihood?
So the log likelihood is what the chi-square test is based on. So because both AIC, BEC, all these things, they're based on log likelihood, or to be more correct, -2 log likelihood. And so you can calculate all these measures from log likelihood. And so the chi-square test is based on the differences in log likelihood. So that's why it's printed. But when people report it, they don't. They tend to report just the chi-square test, as you've done, and they don't say the difference in log likelihood. If they do report it, then they would use AIC or BEC, which is basically, because the log likelihood doesn't take into account how many parameters there are in the model, and you can look up the formula for AIC, and I should have perhaps explained to you better, but it's it is it's based on log likelihood, but with some penalties for how many parameters you have in your models. And the Bayesian models have even more penalties for how many variables you put in. And the reason behind that is that more complex models require more assumptions. Yeah. We'll see. We'll go slightly further, and then we'll have a quick break because I know it's quite a lot to digest, and you'll get an exercise at the end. But it's and it's snowing outside, so the Christmas spirit is really setting in. So, just as a write-up, you would say a likelihood ratio test suggested that a model with a fixed effect for the London reading test was a better fit as compared to a null model. Yeah. So then you would have the chi-square from that table and a p-value. That's what people would tend to report in their assignments, and that's also what you might be asked to do for your assignment. So, perhaps I should just break here. So, shall we break for 10 minutes? How long do you need a break for? 10 minutes? Yeah. I know it's quite dry, but we'll get to the ends and then we'll do some exercises. Okay, I'll see you back at 10.
Oh my goodness, it might be a white Christmas.
Let's not get ahead of ourselves.
Yeah, we'll go to
I get to
my phone to be the same.